superconductor qubit, the Cooper pair box. And as I say, on the top right, you can find the paper. It's pretty long paper. So actually, I just follow that paper. So maybe what the difference is that I go to more details, right? So let me see. Where should I start? Kind of lost my cheat sheet. Anyway, so actually this is the one I want to show earlier. Now what we do is with this artificial atom, we call it artificial atom we use the Josephson junction. Why is artificial atom? Because for every atom, right? Because the physics people, they start with atomic physics. All those quantum mechanics, I cannot say that, but they have lots of achievement in atomic physics, in the light-matter interaction, right? To do all those trapped ion and then come up with the qubit, all this knowledge. All this is just like what they discover in the atoms. They have a ground state, they have an excited state, and then keep going on. Now, if you are just a parabola, you have this state, and then you have equal spacing from the ground first excited state to the second excited state. But because now we try to add into the Josephson junction, then you will have a lower level for the second excited state. So the difference is going to be smaller. And then as a result, we will have enharmonicity, and then you will have a better qubit, right? And again, do you see that this is psi, a different symbol than what I use, but that is basically the same, right? And it is normalized. That's why you get 2 and -2. Okay, and what do I want to say here? That's it, right? So let's start thinking about how these circuits work. So there will be a lot of math. But the goal is that you need to follow the procedure. I want you to learn how to quantize a circuit, which I'm also not very skillful. So the simplest or the most common, but not commonly used from educational point of view, is the Cooper pair box, right? So let me draw the circuit. We have a gate just VG. People probably don't call it gate voltage, but just a control voltage, VG, coupling to a capacitor, CG. And this CG is then connected to this artificial atom, where we have the, I want to say something about this maybe. Let me go back. I want to say something. So this really depends, but many people will say this. They will say that if you have a Josephson junction, you just make a cross. If you have a Josephson junction in parallel with a large capacitor, which is, they call it transmon, then they may have a cross with a box. Also depends on people. Some people say that, right? So in my class, you just need to get clarification. So here, I just draw a cross, okay, because there's Josephson junction. And I deliberately add an external capacitor. I call it CS. Okay? But you need to remember that Josephson junction is a what? Superconductor insulated superconductor structure. So it has capacitance itself. It's not just an inductor, right? So I will also just here draw CJ, right? It is small, but I still draw it. I just draw it explicitly, okay? And you need to be careful when you read other people's work to make sure that to make sure what they mean. Now, then I'm going to define a few things. The first thing is the flux. I say it is just a quantity. I call this QC, okay? Measure from bottom to top. And I will explain more later. And then across this capacitor, I also have phi B, not QC, so I have phi C, right? And then from top to bottom, from here, I have phi A, right? So you see I'm kind of doing KCL, KVL, which you are very familiar with, right? From there, I'm also going to say, I'm going to go for KCL. This is plus minus, right? Plus KVL, I mean, right? And then plus minus. I just label in this way, right? And then let's do it slowly. Now, so what happened? What do I want to say? What is this flux? Phi I, right? Where I is ABC, right? I equal to A, B, C. So you have any circuit, you just have the different branches. This is called the branch flux. It's just not the flux that you have in the magnetic field. But you already see that, for example, across the Joseph function, I have the flux that is due to the difference of the phase times the magnetic flux quanta, right? So this is a definition. Branch flux, right? I call this branch flux. And this makes sense because we define it as the integration of the voltage across it as a function of time for each branch, right? So why this one makes sense? You just recall a general electric engineering definition, V equals to d flux dt, right? So that's why we have this general definition. The flux across the branch must be the voltage, you integrate the voltage over time. Maybe not to infinity, actually. My cheat sheet has problem. Depends on your state, right? When you are operating. Let me just call it to a particular time, capital T. Okay? Is that okay? That is the first thing, definition. One. We define, right? This thing, right? Okay. So let's start with the first law. Maybe I also want to say one more thing, actually. Then what do I mean here? It means Vi is also equals to the time derivative of phi I. So I just put a dot here, right? Instead of d phi dt, I just put d phi dot dt. Sometimes I use capital, sometimes I use small, just treat them the same. Okay? So what do we get from KCL, KVL? We have Kirchhoff voltage law, right? We have VA. Where is VA? I did not say VA. Here is VA. Okay, VA. This is VB, the red one. And this is VC. Okay, then of course VA plus VB plus VC must be equal to 0, right? Because you go for plus minus, plus minus, plus minus, go for a root is 0, yeah?
You don't want it to be VC, VB, and VB?
Oh, sorry, yeah. No, I don't want, I just have typo. The left is actually C. Thank you. The right is A, yeah. So VA plus VB plus VC equal to 0, right? Now, then what is VA? VA, we just say that it is equal to the flux derivative across A. And what is VB? Is the flux derivative across B. And what is VC? What is VC? Do I do something wrong? What's VC based on this figure?
VC VG.
Yeah, you can say the flux derivative, but because I already VG, that is the variable we are controlling, so I just do VG. But looks like, I don't know what my cheat sheet, I will just keep deriving, right? In my cheat sheet, I say this is VG. But it should be negative VG, right? Plus minus, plus minus, plus minus, correct? Or I can put the other side, VB plus VA equal to VG, right? So I'm sorry, maybe I should check the paper one more time, but I will just put minus VG for now. I think my cheat sheet is wrong, right? But do you agree? I think it's minus VG, right? Based on this KVL. For example, if this is 5 volt, this is 2 volt, this is 3 volts, then 5 volts equal to 2 volt plus 3 volt, right? And my VG should have positive on the top, right? But now I'm defining VC as, yeah, so as VB and VC, yeah, VC and VG has opposite polarity, right? So let's hold on. I don't know why I put plus, but I think it should be minus. But we can check that paper to confirm, okay? Now, that is the first thing, KVL. Then we will go to KCL. The KCL tells us that IB must be equal to IA, right? So IB, of course, we're talking about the current going in this direction. We follow the flux, right, this direction. And we also know that we are going to define one thing, define a capacitor called the summation capacitance equal to CS plus CJ. Okay, so this one plus this one, they are in parallel, right? So we just call it, just sum them together, right? CS plus CJ. So let's look at this one. Let me change color. Then what is QA? What is the charge on the A branch? The charge, of course, equals to the C summation times VA, right? It is just like I have capacitor. So what is the charge across this capacitor is the summation times VA. And VA, as we said before, is just equals to the flux time derivative, okay? And I'm going to do the same thing for QB. QB, of course, equal to the CG times the time derivative of the flux, right? What I'm doing, this is just CV, right? This is just CG times VCG, right? It's just like the charge, the capacitance times the voltage across it, then I get this, right? So that's why I'm trying, just because I then want to, this is the way to do that. I first find out the charge. And how about, because I'm doing this KCL, right? I need to find the current, so I find the charge first. I also need to find the current, because for KCL, this is IB, this is IC. Now I only address the charge across the capacitor, but how about the current through the Josephson junction? I have IJ equals to IC sine phi A. Right? It is equals to the phase difference across the Josephson junction, right? This is the phase, this is not the flux. Is this okay? Remember the Josephson junction first equation? Critical current times sine the phase across it, right? But phase is not the quantity we want, right? The proper conjugated variable is the flux. So what we need to do is just change it to the flux across A, and then divided by the reduced flux quanta, right? So I need to multiply by 2 pi also. Right. Maybe confusing. Let me just quickly remind you so you know what I'm doing. Again, the current is I times the phase difference. But I don't want to use phase. I want to use the flux. because that is the conjugated variable we are playing with. So, but I know that the flux equal to the phase times phi 0 divided by 2 pi, right? So instead of put phi, I put 2 pi, also phi, capital Phi, divided by the phi naught, right? Then that is what I'm doing here. Instead of putting phi a, I put phi a times 2 pi divided by phi naught. Okay? If confusing, just make sure that you understand we are trying to express it as the conjugated variable. Then what do we get from KCL? So by KCL, we say IA this one, maybe I'm too full, safe space. Just the total branch, right? IA, the branch go through IA is equals to the current go through the Josephson junction plus the current go through the capacitor, this capacitor. But the charge is QA, right? So it is the time derivative of this capacitor. Both capacitors, so that is the summation, right? So it is equal to flux A time derivative. Is that okay? And this IA must be equal. I think I have many side problem. I just do it on the fly then. I also have this one wrong in my cheat sheet. I will just keep this. Then IA equal to negative IB. Right? So I come up with an equation on this, which I relates the generalized coordinates of each of this branch together. And here I relate, but here is the second derivative, right? Here I also relate it to the gate voltage. Okay? And then my goal is to eliminate the phi b. I should have done it here then. Thank you. Thanks for catching me. It's equal to IB. I'm sorry. Equal to IB. Yeah. Because I already took IA equal to IB, right? That's why, so my cheat sheet was correct. Okay, great. Thanks for catching. Yeah. So IA equal to this part and IB equal to this part, right? And then I'm going to eliminate IB from here. Maybe I will continue to write it. Very sorry for this mess. I'm writing too large. So, pen. So eliminate phi b. Right? How do I eliminate phi b? Here, give me phi b. Phi b equals to Vg phi b dot equals to Vg minus phi a dot. Right? And I only have phi b dot dot, so I need to apply dot dot to it. Right? Phi b dot dot means the second derivative, time derivative of phi b, right? I only have phi b dot here, right? Maybe I can go one more step. Then phi b dot dot equals to Vg dot. Vg is not a constant, right? We're applying gate pulse to it. Minus phi a dot dot, right? So this is equation 1, for example, using equation 1. Right? So with this, I get, yeah.
Sorry, it's been a while since I've done these rules. Isn't just like the current through the capacitor, isn't that just dq dt?
dq dt, yeah.
So then I'm trying to figure out where the C sum with the.
Because Q equal to C sum times VA times flux A dot.
Oh, okay, I see.
So you dq dt, then I have C sum A dot dot.
Got it. Okay.
Yeah, very good question. Yeah. I know this is very confusing and difficult to see for this dot. Is everyone okay with this? Okay. Yeah, question?
One question, like, which one
Yeah. So how about this? I call this IB, and then the whole thing here, IA. Okay, the IA is a sum of the current going through the Josephson junction and this shunting capacitor. Yeah, and that's why the IA is what? IC, right, Josephson junction current, plus the current, which is CQ dot. And CQ dot is C phi dot dot, right? Because, not CQ dot, sorry, CV dot, right? And CV dot is C phi dot dot. Is that okay? Charge. Current is Q dot, dq dt equal to current. But the Q equal to C times V. So it's C times dV dt. But here we show that the V is d phi dt. So it's C times second derivative of phi. That's why we have C phi dot dot. Yeah.
different is the BV dot QB equals to G.
Yeah.
Yeah, that one, what is that equal to BCG?
Yeah. So what do I call this? What I'm trying to say is the volt. So actually, I try to say this is the voltage across this capacitor. So it actually equal to VB. I should just say VB. Yeah, thank you. But at that time, I forgot this notation. I just want to say it is the voltage across capacitor CG. So of course, voltage across capacitor CG is VB. Yeah, sorry for this. Okay? Yeah. Equation 1? Yeah. So you start from here, right? V plus B plus VA plus VB plus C equals 0. But VA by definition is the d phi A dt. So one dot, right? So you just rearrange it. You have phi B dot equal to VG minus phi A dot. Now, then I just take the second derivative. Then phi B dot dot equal to VG dot minus phi A dot dot. I just take second derivative for everything. Yeah. When you say dot is a derivative against t. X. This is also important to mention. Right? Sorry if I did not make this clear. X dot means dx dt. Whenever you see the dot, it's d something dt. Okay, just a shorthand notation. So now then, the point is here, right? So we use KVL, we put the phi there, and then we use KCL, we just put in all the phi, but now you have a second derivative. You equate the equation, and I'm going to eliminate phi b, which I'm not interested in, right? So with this, I substitute this to here, then I will get this. Yeah, because this is the qubit you are studying. We want to see when we apply the gate voltage, how this qubit change. We don't care about how the phi across this string. It will change, but we are interested in this. right? So with this, you get C summation phi A dot dot plus IC. Now I try to save the space, I just put phi A, right? I use the face instead of putting this whole thing. This whole thing is phi A. Okay? Let me see if I write. Yeah. Then it is equals to phi B. Now it's correct. This is, then you substitute 1 into here, right? Do you see that when I substitute this to here, what do I get? Still wrong. It becomes, yeah, CG times, what is plus? Phi A, I put a negative in front, minus VG dot. Do you see what I'm doing? This is equal, right? This is equal. This is, right? So I just substitute CG, phi B dot dot by this whole thing, but I put the negative in front. So I just swap phi A dot dot and VG dot. Make sense? Now, however, because of this mistake, I have a sign difference from my cheat sheet. So I will go back to check, but maybe it's just a different definition of VG, right? So let's keep this. If I say something wrong, I will fix the slide, but I think you understand. It's just a flipping of sign. Okay, so now we have this equation, all in phi A, right? What is phi A again? It's the position, right? So then, what do? Just recall, phi A, phi is the position. So what is phi A dot? It's the generalized what is that? Velocity. Very good. And then you probably have something in your mind already. What do we want to construct now? The Lagrangian. Because if I can construct the Lagrangian, I can construct the Hamiltonian. Once I construct the Hamiltonian, I will do quantization. I promote the position to what we just discussed, promotes the momentum to what we just discussed, then we quantize the circuit, right? So we are trying to find the Lagrangian, L. What is the Lagrangian of this circuit? Not this circuit, of this qubit, right? So the Lagrangian is going to be the total, let me just copy it down, right? CV squared of the capacitor Let me jump this step. Oh, actually, I cannot construct. I'm sorry. So how do you construct the Lagrangian? You need to guess the Lagrangian first. Okay. So I need to make this very clear. That's why I got lost. I guess, maybe I guess how do you spell that? G-U-E-S-S, right? Guess the Lagrangian. Because I want to find the equation of motion. So I'm going to give this to you. But you should be able to guess, right? Of course, in your exam, I'm not going to ask you to guess. But that is what you do if you do the research. You need to guess the Lagrangian based on intellectual guess. This is the Lagrangian of this circuit. Okay, this is given, right? And you guess. But how do I check if this is correct? I'm going to check the equation of motion and make sure it is the same as what I had before. Okay? So actually, I forgot to emphasize one important thing. What we get here, this one, is the equation of motion of this system. Right? Because I correlate how the generalized coordinate changes as a function of time. Okay? So, but then I want to construct the Lagrangian so that it reproduces the equation of motion. So I'm going to check if my guess is correct. How do I check? I just remember the equation, d dt, partial L, maybe I use curly, partial L, partial t, minus partial L, partial q equal to 0. Okay? And I remember what is q. No, not partial t, sorry. This is partial q dot. What is q in this case? Of course, it is phi a, right? And what is q dot in this case? It's just phi a dot, as what we said here. Is that okay? Right? So what I did is I used KCL, KVL to come up with the equation of motion. And you actually can solve it already. But however, it is not quantized. It's useless. That's why the second step is that I need to guess the Lagrangian. And if you're familiar with the math, you probably can guess it right away. But here I just give you, right? It's given in the paper. But then the second thing is you need to check to make sure this is the correct Lagrangian. So we will plug into this equation, right? So what is d dt partial L partial phi a dot? Right. Of course, this is equal to d dt, and then the whole thing. So I try to do partial L partial Q dot, which means I try to do partial L partial phi A dot, right? Which one depends on phi A dot? This one does not depend on phi A dot. This is phi A, right? So this is the velocity. I only care about the velocity. So the first term give me C summation phi A dot. This is the first term. The second term give me CG phi A dot plus phi C dot. I have so much problem in my cheat sheet. Is that okay? Did I make any mistakes so far? No, right? Looks like I'm okay, right? I'm a little worried. My cheat sheet has a lot of error. Now I'm going to do the second derivative. I'm not second. Then I apply d dt to it, right? Then this is what I will get. Dot dot plus phi c dot dot. Yeah, okay, that's right. She should just wrong. Okay, now then how about the partial L partial phi A? The first and second term does not depend on phi A, because first and second term are the generalized velocity, right? Only the last term depends on phi A. And the last term is what? Cosine, right? So it is EJ sine, and then phi A. This time I want to spell it out. This is phi A 2 pi divided by phi naught. So on the in front of it, I need to take out this 2 pi phi naught, which I can put it back as negative EJ 2 pi phi naught times psi, and then I use the phase again. I just group everything into phase. Okay, this is sometimes confusing, right? So based on this, what is the equation of motion? It is C summation phi A dot dot plus, not plus, should be, yeah, plus. Because this is minus, right? Minus partial L partial Q. Do you see that in this equation of motion? I try to take this term, C summation phi A dot dot, and then I need to minus this whole term, right? And this whole term is negative, so it becomes plus. Plus EJ 2 pi over phi naught times psi phi equals to negative CG phi A dot dot plus phi C dot dot. Now, but what is EJ times this term? This term turned out to be IC. Right? If you forgot, look at this again. Look at this equation. Oh, I did not put here, however, right? It was in the last line. But anyway, you trust me. EJ times this guy equal to IC, right? So I get back the same equation as here. If you go back to the previous line. Negative CG phi A dot dot plus phi C, negative CG phi dot dot plus phi C, because phi C is just equal to negative VG. Is this okay? Right, so basically what did we do again? We use KCL, KVL to get the flux and also the charge. But we eliminated the charge because the flux is what we're interested in now. To get the equation of motion, because the flux is the location, is the x, the generalized coordinate, we get is velocity. And then I come up with the Lagrangian. This is just because I'm going to guess it. After I guess it, I just check it, right? And I do see that I put into the Lagrange equation, I get the correct equation of motion. So this is the correct Lagrangian of this system. Is that okay? I know it's very confusing. I do want you to swallow it, to really go through the step, right? So it's already time's up. But you can guess what I'm going to do next. Now I have Lagrangian. You can create a Hamiltonian, use the Hamiltonian equation. Once you have a Hamiltonian, then you use the momentum and position to do quantization. And then you get the system you want. And then we start playing with this Cooper pair in a box. Okay? So let's stop here. Yeah.
Is there no formula to write out the potential, or ideas right now? Because if you look at the Lagrangian that you